Of course, they will all the classes will be recorded. Yes. So, okay, well, let me just tell you the basics. So, first of all, my name is Apurva. And this is MA219. Yes, this is linear algebra. And, okay, so this is the meeting time. And now, yeah, the first and foremost thing to do is to talk about the format. So, we tried this last year as well. It was actually I who taught the same course last year, also online. And eventually, as you know, the policy, I think, is because people may have unreliable internet connection or other things. So the policy is to record all the lectures. So what I planned, and then of course, yeah. So what we did last time, and it seemed to work fairly well, was sorry, 1 second, was to record and put up the videos on some kind of a Google Drive. Yeah, so all of us got some Google Drive, so accounts. So yeah, what I recorded with was Google Meet, and that seemed to generate a clear but low size thing, which is more convenient to people, I guess. Well, that was the policy, right? If people have some spotty internet connections or stuff like that, or poor bandwidth, then downloading a low size file is better. So that was what I had done last time. And so the way we worked this out was that I would record the videos, maybe something like 1 day in advance, put them up, and then you guys get to, well, then you can see them when you want to see them, of course. It's entirely up to you. During the times of the classes, which are the meeting times, are Tuesday, Thursday, 8:30 to 10. So during these meeting times, we would, I would be online one of the 2 days, and one of the TAs would be online one of the 2 days. And then, yeah, if people had any questions about the lectures, they would come and ask. And I think I got like maybe 5 questions in the entire semester or something like that. I mean, I think the reason why, I mean, clearly I'm a wonderful lecturer, so that's why I got no questions. But the reason I think why I got very few questions is because, first of all, this is a basic course. I mean, it's just matrices. Everybody might have even seen matrices in high school, let alone college. But not only that, for the undergraduates who are taking this class, especially the mathematics, well, actually all undergraduates who are taking this class or attending these lectures, you have already basically seen, I think, like 70% of the course in your UM 101 and UM 102. I should know because I taught UM 102 a few years ago, and then when I looked at the syllabus, I was like, well, this seems like exactly the same thing, or a bunch of it. So yeah, there is lots of talks going on about how to, like change this to change the situation, especially for the undergraduates. Like you should probably see something with more different material. And maybe I would have done something more about it, me and a couple of others who have taught this course before, but then the pandemic happened and everything was shelved. But maybe now life is slowly returning back to some kind of normalcy, and you guys won't benefit by it, but maybe your next batch of undergraduates will see a course which is very different, or at least doesn't repeat all the same things. So my guess is because of that kind of thing, and in general, right, everybody else who's not an undergraduate but is taking this lecture has probably also seen some variant of linear algebra before. The only difference being you might have seen it over real numbers or complex numbers at the most. So Hermitian, symmetric matrices, orthogonal matrices, which we won't cover in this course. As far as symmetric matrices, yes. Orthogonal matrices, likely not very much. But we will cover it over general fields. And so that's the difference. And then there are some, the nice thing is that most of the proofs that, well, okay, a bunch of the proofs that you might have seen before do go through. Because, so for instance, when I studied linear algebra in college, I studied it directly over general fields. And so all these proofs go through, and those are the ones I want to tell you about. But so that's what the sort of thing was last time, and it worked pretty well. It seemed to work pretty well. So let me get a new. Yeah. Okay. So that's what I propose. And so again, one of these times, which is, I think I already put this online. On Thursday, I will be online. On Tuesday, one of my TAs, Demal Loshain, will be online. And there's also another TA we have, Annapurna Banik, and she will be available on Mondays for another 90-minute session. So are these, if Devmallo and Annapurna are online, maybe you could just unmute yourself and say hello, or unmute your audio and video and say hello.
Yes, Devmalya here, and I am following your words, and I will be here on every Tuesday.
Great, thanks. I don't know if Annapurna is here, but if not, she
Sir,
will be.
yes, sir, I am. Annapurna is here.
Ah,
So I will be online on the Mondays from 4 to 5:30, I think.
that's right.
Evening session.
Great. So of course, again, this is also useful for obviously if you have questions about the homeworks, questions about something said in class, or in general about something else in linear algebra, or you can talk to me about other mathematics. I can't guarantee I can answer your questions, but yeah, then come online, talk to us, and yeah, we are available. Also, obviously by email. If you have other questions at other times, you can contact us by email, and we can try to help you out. Okay, so that is that. That's the format. We'll meet. So the lectures will be basically 2 lectures a week, 90 minutes, and you guys are free to see them at your own leisure. Homeworks typically, so I think I even wrote this down. Last time I proposed something, but everybody kept extending it. Like last time, I think the homeworks were due on Monday night or Tuesday night. But then almost every week, at least one student requested me, can they push it to Wednesday night or Thursday night? So this time, I'm just doing this on Thursday night, and there are no extensions, please. Okay, so there's plenty of time. So homework. So I'll just mention some of these points. All of this is on the handout, and this handout is already present on the course website. So and the website was in the email. It's like a Russian doll sequence, right? So go to the email, go to the website, go to the handout, and find out what's said there. But yeah, okay. So maybe I'll go over the handout from the top. Right. So first of all, the course, the name of the instructor, the TAs, their office hours. Clearly, the room is just online because now there are no rooms. What else? Let's see. Okay. Next is the office hours. So the office hours are on Microsoft Teams. Yeah, it says the credits are 3+1, but I mean, I already talked to various relevant people, and yeah, that's fine. You just need to attend the classes, and if you have questions, go to the office hours and so on, and we'll figure it out as the semester goes on. Okay. For now, yeah. For now, as far as I know, it's classes. Okay, great. What next? I have a phone number which obviously is here, and none of us are here unless we need to teach or record or something. So email is the best way to reach me, and your TAs. The email addresses are mentioned. The course website. Okay, the syllabus I'll get to later because we'll start discussing the mathematics. The textbook. Well, linear algebra is sort of, it's standard to every sort of, science and engineering discipline, especially at IISc. So everybody here knows and has learned linear algebra in their own way, and like most faculty at least, let's say. So, there really isn't a very standard textbook, but this is sort of by and large the accepted one over here and sort of anywhere else in the world. So I'll mention it if you want to look at it for like clarification on concepts, for exercises to try out yourselves, and so on and so forth. Okay, so Hoffman and Kunz, it's obviously mentioned here. Michael Arkin's algebra is there. Paul Halmosh is there. There is another book that's more recent called Linear Algebra Done Right. I haven't looked at it, but I'm told it's a wonderful book. Feel free to look at it and use it. Okay. The homeworks, exams obviously will follow the content that we cover in the lectures. So so the nice thing about pre-recorded lectures is, if you feel it's going too slowly, then you can just, forward it every 5 minutes, look at everything written on the board, figure out if you understand it, move on to the next 5 minutes, and so on. If you want to speed view your class, if you think you've already seen it before. But of course, yeah, I do tell you again that we will cover everything in full generality over general fields. So that already might be something that you might not have seen before. If, of course, there are, I understand, Algebra 1 students here, and they will be looking at general fields, obviously, in their course, but maybe slightly later than we will. Because you guys, the Algebra 1 students, will start with groups and rings first and then fields. So we start with fields first and don't do groups and rings. Okay, the exam and the credits for the course, homeworks and quizzes are 50%. last time we had one quiz, and this time I might not even have any quizzes. You know, it's a hard job, you know, like for you guys especially as well. You know, like either at home or stuck in your dorm rooms here, and let's yeah, and I'll probably only have homeworks. Then that's about 50% of the credits. The midsem, there is one midsem. I put down the date of September 23rd, but that is completely not my decision at all. This is just like a placeholder. It's my like guess as to when it is. The point is that this is a math department course for math majors, like math honors students, and for integrated PhD students of mathematics, among others. Of course, people from all departments are welcome to and do apply and do take the course for credit. But because this is a math major course, we are obliged to hold all our midterms in the same week. And that week itself gets decided not by me. It gets decided by the maths major or the PhD coordinator of the department. And he will let us know maybe around the end of August or something. When is the week? So my guess is it's September 23rd, but it's probably that week or the week after that. And we will find out. So that may be changed. The final obviously is an institute-wide decision. It's not even in the hands of our department. So I didn't even bother guessing when it's going to happen. Okay, homework. The one policy you should know, obviously. So I will assign homework. So this is what I want to write down. Homework assigned weekly. Okay, it might be updated on Thursday as well. So I might assign it on Tuesday and update it on Thursday. Sometimes. The deadline to submit it is the next Thursday night. That means you have 3 sets of office hours to, you have the whole weekend and then 3 sets of office hours. Monday, Tuesday, Thursday morning. Sorry. So due. Let's give some decent time. I mean, I don't want it to be that well. Thursday. Okay, off next week. Okay, it's basically by Thursday midnight, it's due. And this is really a hard deadline. I mean, it should really have been due. I mean, by the time, so I assigned the homework on Tuesday already. That can be asked on that very Thursday. And then that was what we tried to do last year. And then, so I was always saying, let's do it due on Tuesday nights. You still get 3 office hours, but then every week somebody or the other had some other constraint, and so can be extended. So let's just agree to do this. And this was the hard deadline last year, so let's keep it as a hard deadline this year, and just keep that as the deadline itself. No extensions, but nothing less. Okay. And obviously, you must have heard this from everyone else before, but yes. You are free to discuss homework solutions among yourselves and with the TAs and with me, but please write the solutions independently in your own words. Okay? Again, please write them independently in your own words. This is important because, well, first of all, you should learn the subject. But second of all, obviously, for exams, right? You have to write independently in your own words there. So do it here as well. Yeah, so for both reasons. Fine, and then there are various other things. So yeah, so emails, when you email either the TAs or me, write MA219 in the subject line in addition to other things if you want, but MA219 will be useful. Exams, there are no backup exams. Please be available wherever you are for the midsem and final. Office hours, well, yeah, so we are available in office hours. Yeah, and we'll see how to do that. Yeah, there is some ethics page, which again, in addition to writing your solutions independently, you should read the ethics page. Okay, before we go on to the math itself, are there any questions? If not, probably the TAs don't need to be here. Okay, and so today's lecture, I mean, so I'll assign homeworks this week, but yeah, I'll cover some mathematics today, but basically in principle, we will start the class on Thursday itself, with the Thursday's lecture, which I will post on. The other advantage of that thing was, well, the other nice thing at the end of the course was I could give out a set of course videos, like the entire folder I could make available to all the participants. Although because last time I taught the course was the first time I taught it in I think 10 years, and the first time I taught it in India for sure. So yeah, there were a bunch of polishings that I had to do. Sometimes I had to email the students after a lecture, say, okay, please skip minutes 30 to 41 of the lecture, because I tried something ambitious and then went back and backtracked it and then came back the next day and polished it. So hopefully I will hope to avoid all of these things this year, because I already have experience from last year. But anyway, so at the end of this, you should hopefully have a nice set of videos as well. Okay, so if there are no further questions regarding the logistics, then the TAs can leave. Thanks. Okay, so if they wish. Okay, so the idea is to see linear algebra and over a general field. So some of you, or many of you, or most of you, may have seen this over R or C. But that is just a special case, and a bunch of the results that you would have seen go through. Obviously, some things like the spectral theorem may not go through, and we'll get to that. So things like that at the end of the course. But first, we will try to cover everything that does go through. Okay, so there's a bunch of topics listed in the syllabus, which all of which I'm supposed to cover. So yeah, so vector spaces, obviously, and so on. Linear transformations and matrices. Rank nullity, column space, row space, null space, this, that, yeah, dual spaces. Some things that we will extra cover in addition are things like dual spaces. We will cover the direct sum of vector spaces, which you may not have seen. We will cover the direct product of vector spaces, which you may have seen, and how dimensions behave, or how we might cover tensor products of vector spaces, which you may not have seen. Okay, then there are things like, so obviously linear algebra, if you ask any school student, if you had asked me in high school, or maybe for middle school or high school, whenever we first see matrices, what is linear algebra about? I would have said it's about matrices. And so what are matrices useful for? Well, the conventional definition in CBSE was to record a set of data, right? Some prices versus months or some interesting thing, which is correct, which is of course correct. It's like matrices are arrays of numbers or tables of numbers, so you tabulate. But it's much more than that, right? Just because you can arrange numbers in a way, you can do many more things with that. So, for instance, if you have the price per unit in a row vector, and you have number of units in the column vector, and you take the dot product or you take the matrix product, then you get the total price. So if you have, this is literally my class 9 or class 10 or whatever CBSE example. Right? If I arrange if I have a bunch of items and whose price per units I know and I have those many units, then I know how to calculate this thing. That might even have been in the CBSE book. I was a CBSE student. Anyway, so so of course you can do much more than just systematically record data in arrays, in matrices. You can actually work out more things. There are interpretations. Like there is an actual real-world interpretation of this mathematical concept, which we call the matrix multiplication, or the inner product, or the dot product. Right? So things like that. So of course matrices are useful, but the sort of in college, maybe the first and foremost thing that you see that people would have seen is, if you are given a matrix, you would like to solve a linear system, AX equals B, and then find out how many solutions there are, if there are any solutions at all, and so on and so forth. So that's also another thing we will see, solutions of linear systems or equations. One interesting thing that shows up in that system, that set, is when is a matrix always guaranteed to give a unique solution? That leads us to the world of invertible matrices, and there is a very almost, I won't call it magical, but it's a very remarkable map or a function that assigns to every single matrix a square matrix, a unique scalar in that field, and not just over R or C, but over any field. And that tells you that if that scalar is 0, for every output vector, you get a unique input as a unique solution of the linear system AX equals B, if and only if that scalar for that matrix is non-zero. And that doesn't depend on the output vector at all. And that's called the determinant. So we will see properties of determinants over general fields. Cramer's rule, which you have seen in school. And then we'll get to things like the Cayley-Hamilton theorem, and then the Jordan canonical form, and so on and so forth. Okay, but in addition to, as I just said, that in addition to, so if you want to solve linear systems, solve Ax equals B, right? And suppose my A was A is n by n, meaning it's a square matrix, then there exists a unique. I hope people have seen this kind of notation. This is there exists, and this is unique. Some number called C in the ground field. So this is sort of warming you up for the kind of notation we will use in this course, right? So we will use formal symbols, obviously. So there exists a unique constant, a scalar belonging as an element of the ground field. F is a field such that what? Such that Ax equals B has a, sorry, I should give myself more space. Such that Ax equals B has a unique solution for all B in F to the n. This is the symbol for all, if and only if, and this C is non-zero. And this C is of course called the determinant of F, a determinant of A. Well, that's a very remarkable property. Okay, so similarly, but this is true for square matrices. We will see another thing which you might already have seen in UM102, which is for rectangular matrices. I'm saying UM102 because this is for the people who have taken UM102. For others, you might have seen it in your college's analog of UM102, something, or in your analog of linear algebra. That even for, but you see here there is no restriction on solving Ax equals B for square matrices. By the way, if you haven't seen this before, don't worry. We will obviously do all of this in full detail. This is like I don't know, a trailer or a preview or something, and maybe even like all these Marvel movie trailers, I will give you a bunch of things in complete out of order, so that you're completely confused about how the movie is going to go. But then after seeing the rest of the syllabus in the whole semester, then you will hopefully get a more linear sense of things. But like Marvel trailers, this trailer might be out of order. Okay, so I shouldn't malign Marvel. Every Hollywood movie does that. So anyway, especially the thrillers. So okay, but now from the next thrilling part. So this is of course the point is linear systems don't need to be square matrices. They can be rectangular. Right? So then I would have something like A, which is the n cross n matrix, times X, which is an n cross 1 vector, column vector, equals B, and this B would now be an n cross 1 vector. So here, regardless of what M and N are, so for every matrix of every size over every field, for every square matrix of every size over every field, there is a unique scalar with some satisfaction, something with some nice properties. For every matrix of every size over every field, not necessarily square, there exists a unique another matrix, which makes it much easier to solve this system. There exists a unique B, let's call it n cross n. Again, I'll just say which encodes the same information or which can be used to tremendously simplify solving the system. Oh, I should also therefore tell you the name of that B. So B is called the row reduced echelon form of A. Okay, so that's what B is called, and so we will see this as well in the later in the course. In fact, solving linear systems is probably the first thing we will see. Well, the second thing. So after first of all, I want to define for you what is a field. And then I want to define for you what is a vector space, because the definition is almost exactly parallel to a field. Once we do that, we'll see some examples and so on, and then we'll get to solving linear systems over general fields, and that's when we will see this thing. Sorry, excuse me. Okay, what else? Yeah, we're supposed to talk about symmetries and groups of motions on the plane and so on, but I don't know if I will have time to talk about that. Maybe I will. We'll see. I do want to talk about bilinear forms, though. So, for example, for real symmetric matrices or complex Hermitian matrices, we have something called these are square matrices where the transpose equals themselves, and then even before that, I don't know if I said that we will talk about eigenvalues and eigenvectors. These are really, really crucial. Yeah. So, given square matrices and so on, one important, very important polynomial. So, I guess you all have seen polynomials. If you haven't, we will see them, of course, in this course. One very important polynomial is something called the characteristic polynomial of the matrix. And the roots of this polynomial are called the eigenvalues of the matrix, and they encode some very nice things about this matrix. And if you have seen the movie The Matrix, then 20 years ago, I made a very, very bad pun, a mathematical pun about eigenvalues and eigenvectors, which if we have time, I will tell you. But only after we do eigenvalues and eigenvectors. Okay, so then, once you know eigenvalues, eigenvectors, we will talk about the spectral theorem for symmetric matrices, or more generally for normal matrices. So it's not just true for matrices which are equal to their transpose, it's true for matrices which commute with their transpose. Something like that. Yeah. Right? So they don't need to be equal, but just A transpose equals A transpose A. These are called real normal matrices, and the spectral theorem holds for those. Okay, so these are some of the things we will see, and let me even get to sort of a more concrete kind of questions I wrote down, which we will see. So let's see. So for example, we will see things like these. So some other things that we will see, or at least if we don't see, you will know how to work out by the end of this course. One is something like this: every polynomial something like, let's say, ax cube, ax, let's say ax6 plus bx5. So 6, 5, 4, 3, 2, 1, 0 plus fx plus g. And there are 7, so x to the 1 and x to the 0 has at most 6 groups. Okay. So why is that true? Well, you can answer this using linear algebra. You can answer this using something called a determinant. We will see why, or if you don't see why, then I might ask you in the homework why. Okay, that is one thing we'll see. Maybe I should number these for fun. 1, 2, 3, 4. Okay, what else did I write down? So for instance, we will also see why the Lagrange. So given if you have a bunch of data points, x1, x2, xn, y1, y2, yn, you want to fit a polynomial to them, then there is a unique polynomial of degree at most n, or n minus 1, something like that. N minus 1, because for 2 points you have a line, which is degree 1. So uniqueness of Lagrange polynomials, Lagrange interpolation polynomials. Again, this is explained using the theory of determinants again. And then there is, so this one actually absolutely fascinated me when I first saw it, and I've never forgotten it, of course. You might have seen the Fibonacci numbers. So these are Fibonacci numbers, right? So this means you start with 1 and 1, and then every next number is the sum of the previous two. You get 2, 1 plus 2 is 3, and 5, 8, and 13. And of course, if you have read the Da Vinci Code, then you know that these are the secret to the Holy Grail, like the location of that. But apart from popular books, The point is, of course, so let Fn be the n Fibonacci number. One can find an explicit formula for it. Using matrices, using eigenvalues. So if you again haven't seen this before, then this is again a very remarkable, it's a beautiful theorem, of course. The fact that you can find a closed form expression, I saw this in school first, in high school again, just before college. It was wonderful. Yeah. So yeah, but you can do this using again 2 by 2 matrices, nothing more than 2 by 2 matrices. Very, very simple stuff. But you need to know what are eigenvalues. So we will see this, we will see eigenvalues and therefore this. Actually, that reminds me of a forward I got on WhatsApp University yesterday. It's not my notation, WhatsApp University, but it's very apt. It was called Fibonacci soup, and the idea was the ingredients are yesterday's soup and day before yesterday's soup. So enjoy. The next one we have is, this is a very interesting fact. Suppose I have a 4 by 4 matrix. And suppose I know is such that A raised to 15 is the zero matrix. So okay, there is a way that you can multiply matrices. So they take this matrix, multiply it by itself 15 times. You get 0. Like every entry is 0. Then you can already prove that the fourth power is already 0. You don't need to multiply 15 times. Again, something that one works out using something called the minimal polynomial and the characteristic polynomial, and so on. Next, there are a bunch of these nice things. Another one is if some of you like to solve differential equations or systems of differential equations, then you can solve something like this. So if you have two variables, x of t, two functions of the time variable, let's say. So I should say not solve, but solve for. Right? The system which is that x prime of t equals, let's say, 5 x of t plus 7 y of t, y prime of t equals 7 x of t plus 5 y of t. And yes, it is indeed possible to solve this equation explicitly. And if you are given some boundary conditions, then uniquely. And then we come to, so this is all sort of getting more towards the analysis side. This was something combinatorial. This is again maybe some analysis. This kind of thing actually holds over every field. So it's an algebraic phenomenon. And let me end with a couple of other algebraic, 3 and 4 are both algebraic because they work over every field. Actually, so does this. We'll see that. Okay, this is combinatorial. These two are like analysis. Let me end with two more algebraic things. Well, the same thing, but so there is something called finite fields. So maybe I should start by saying what is a field itself. We will define these maybe. I would like to define this today. So let's do this today. But yeah, after that, let's see. So. Maybe today let's actually do some math. But I'll define a field which is available in infinitely many places on the internet. It's in Wikipedia. Okay, so yes, as I said, we will work over a general field. Okay, in this course. So let's see. So maybe I should start by defining the field then. So So here is where our course formally starts. Right? So let me define the field and then let me tell you 2 or 3 things that you will also see later in the course. But it's very easy to state those 2 or 3 things, but to prove them you require the idea of vector space and dimension and basis. And so that's why it's not immediate, the 2 or 3 facts that I will tell you. But basically, okay, so informally, a field is just a set of numbers where you can add, subtract, multiply, and divide by anything that's not zero. So for example, the integers, the 1, 2, 3, 4, 5, -1, -2, and something, you can add, subtract, and multiply, but you can't divide. 1/2 is not a number, it's not an integer. So the integers do not form a field. But the set of fractions, of course, do form a field. 1/2 is a fraction, and you can multiply fractions, you can divide fractions, and so on. That's a field. The set of real numbers is a field, the set of complex numbers is a field, but there are several other fields. There are even fields which consist of finitely many elements. Okay? Not just infinite fields like reals, rationals, and so on. So now that was the informal definition, where you can add, subtract, multiply, and divide. It's just a number system where the 4 operations of arithmetic hold. But now let's write it down formally. So a field is a set which I will call as F, together with a bunch of different now let's see. So there are some things for addition, which is the plus operation, the 0 element, and the negative. Then there are some things for multiplication, the times operation, the 1 element, and the reciprocal. Okay. And I think that's it. Satisfying the following. So let me say here. Let's write down what all these things are. So, okay, so first of all, 0 and 1 are 2 elements in the field. Okay. Okay, this bullet point is going to be a hassle when I write the star, when I write the times. So let's see. The next one, 0, 1, plus and times are operations. Let's call them as our functions, our maps from F cross F, meaning that each of them takes 2 inputs and gives you 1 output, A plus B, A times B. And the result must also lie in the field. What next? Then you have the minus map, is a map from every element of it. So it takes an element of your number set of numbers and gives you the negative. And I have to do this separately for this one because can anyone tell me why? You can unmute and tell me. Why am I not? So I can see 0 and 1, the additive and multiplicative ones I put together. Plus and dot I put together. But minus and reciprocal I'm not putting together. Can you see why?
You don't have a reciprocal for 0.
Thank you. Right. So therefore I can't say this is also a map from the same domain. So I have to say something like F minus 0 to F. And in algebra 1, for those of you who take it, you might see this as the set of multiplicative units, and it's called F cross. Okay, this is just what the maps are, the domains and the codomains, but now there are some conditions that these maps satisfy. And these satisfy the following conditions. Okay, so here we go. And you have already seen, of course, all of you know these conditions inside out for real numbers, or you wouldn't be taking, or you shouldn't be taking this class. But I'm sure all of you do know this. But yeah, so so here are the conditions. Okay, so maybe I can even write these down in parallel. Plus is commutative. Meaning so A plus B equals B plus A, for all A and B. And the same way, let me lump them together. So dot is commutative, A dot B equals B dot A. I'll just do that the same. So addition is commutative. Similarly, addition is associative. You can multiply two numbers, so you can add two numbers in either order, it doesn't matter. Similarly, you can multiply two numbers in, you can multiply three numbers. Well, I really shouldn't say this. This is a college class, not a school class. Okay, so A plus B. The point is, okay, maybe I should say this, not associative means. The point is, this is not a priori defined. It's not a priori well defined because there are two pluses. So each plus is operation taking two numbers. So you have to decide which one you want to do first, get some scalar, and then add that to the other number. So you write this on both sides, but you put the brackets differently. So first you add this and then this, or first you add this and then this, and this is the same. And similarly, times is associative. A dot B dot C equals A dot B dot C. Again, for all ABC. Okay, the third one, so that's commutative associative. Now we get to the units. There's the multiplicative, so there's additive identity. So additive slash multiplicative identities. And the use of the word identity here is actually appropriate because they will talk about the identity matrix, which is the multiplicative identity for square matrices. Okay, so identity, this is just the fact that A plus, first additive, A plus 0 equals A, and A dot 1 equals A for all A. Those are the identity maps, the identity elements, and then there are the inverses, additive, multiplicative inverses. So here we have that. So basically A plus minus A equals 0. We already have these maps that satisfy. So the map satisfy this condition. The other way that you might have seen this, or in Hoffman and Kunz's book, for instance, I just checked, was for all A there exists something called the minus A such that A plus minus A is 0. But that just means there's a well-defined unique map. Right? There exists a unique element, so we'll call that as this. Well, now here is what I'm saying. I'm not saying that this is a unique map. I'm not saying this is unique. And am I? Fine. I'll do one of these for you. The point is, I'm not saying this is the unique element that satisfies this, but of course that's going to be in your first homework set. Prove that if there are two elements that satisfy this condition, then they must be the same. Okay? And similarly, okay, this is true for, now again, because of this distinction, I'll put this is for all A in F, and A times A inverse is 1 for all A in F, let's say. This stands for the set difference 0, so F except 0. Okay, so these are the additive and multiplicative inverse identities or definition. And then there are two other conditions. Okay, where should I put them? Well, the fifth one I will put here, and the sixth one I will put here. The fifth one is again something that you have seen in high school, or before high school, I hope. The distributive law. Should really have used less space here, but anyway, fine. The distributive law simply says that A times B plus C is AB plus AC. Okay? Great. Again, this is true for all A, B, C in F. I'll just say this here. Let's call this star, and because I don't want to use up space, just say the same star for all A, B, and C scalars. Right? So elements of the field are called scalars. Okay, fine. And the last one is very simple. These two elements are distinct. Otherwise, you run the risk of sort of everything collapsing. 0 and 1 are distinct elements of the field. So I could have said it here, but no, that's I want to keep it as, highlight it as an axiom of the field. So these are called the field axioms. Maybe I should say that here. These satisfy the field axioms. So this was literally in fact, in my case, this was literally the first lecture I attended after high school. I went to ISI Calcutta, and our professor started. The first thing you will see is linear algebra. So first of all, what are real numbers? They are an example of a field. What is a field? And this was the first thing we saw. Okay. So now let me ask you the second thing we saw, which is what we were asked. As far as I remember, for instance, we were asked to prove. So you see that it says that 0 is some element which satisfies this property. Inside a field, of course, addition is commutative and there is a negative. But even before a negative, you need the existence of a 0. 0 is this element. See, that's all I wanted to do here. So maybe I'll ask someone to prove. So now again, the other thing about this class, of course, is we will be, of course, completely rigorous, and this course will focus on proofs. So I will be proving things for you, not just telling you that you can solve a linear system uniquely or not solve it uniquely and so on. Right? So, so prove for me 0 in F is unique. Meaning if you have two different elements which satisfy the properties of 0, then they have to be the same element. Yeah, anyway. So one way to do it is by something called the method of contradiction. So again, anyone, feel free to unmute it. Unmute and start.
0 plus 0 dashed equals to 0 dashed and 0 plus 0 dashed equals to 0.
There are two. Suppose 0 and 0 dash are both additive identities, then you do exactly what he said. Then let's look at the element 0 plus 0 dash. Right. On the one hand, 0 plus anything plus 0, anything plus the additive identity is itself. So this is an additive identity. So this is anything. So this is itself. On the other hand, since I didn't say it the other way, I'll just say addition is commutative. So I write this as 0 dash plus 0. But now again, 0 is an additive identity. So anything plus additive identity equals itself. And so you start with 0 and you end with 0 dash. And so they are the same. That's right. Excellent. So that's what is. So that these are the kind of proofs. So in the exercises, I will ask you to prove that similarly, 1 is unique. Not only that, minus A is unique for every A, and A inverse is unique. So I didn't say that these are the only ones that satisfy this condition, but just from these axioms, you can reduce that. So the idea will be to prove this. So I won't ask you to state the axiom number A for here and so on, or axiom number C, but write out your working so that the graders know what they are doing. Okay, the TAs know, like that you know what you're doing. And you write it down. Don't say 0 equals 0 dash. That's not. The proof is that 0 equals this, this equals this, this equals this. So, and the point is, it's only for like this week and at the most next week. Beyond that, I won't ask you to explain field axioms because we'll be busy doing matrices or vector spaces and so on. So while you're first being exposed to the field axioms, I would like you to detail the workings of those. So do mention each step. Later on, as I said, basically within the next 2 weeks, I won't probably ask you to write down those steps. Of course, in the midterm, if there is a question like the field axioms, then I would ask you to write down those steps again. So, okay, so that was about the field. Now, let me tell you why the notion of a vector space is somewhat similar. I believe this is also true. Since I don't have space, I'll just write definition. A vector space now over a field F a vector space over a field F is a set with, I'll just call it a triple now, is a set V with a plus 0, that's right, a minus, that is also correct. Scalar multiplication, this is no longer needed, I think that's pretty much it. If I'm not wrong, where, again, now let's see. So 0 is now, okay, let me distinguish by calling this 0 like this. So 0 is an element of the vector space. So, okay, so the elements of the field are called scalars, element of the vector space are called vectors, like R2, R3. Okay, plus, okay, now I need to write these down differently. So now there are these maps, okay, very good. So, I'll just, okay, R maps, I'll reduce the R maps to just is a map. So plus, there are the other three are maps. So plus is a map from V cross V to V. Minus is a map from V to V. And dot is a map. So plus is just you're adding two vectors, minus is you're subtracting two vectors. Well, minus is the negative of a vector. And dot is a map from F cross V to V. This is called scalar multiplication. Scalar multiplication. Okay, and these satisfy the vector space axioms. I'll just say these satisfy. Okay, so plus is commutative. I will call it V plus W. So for all vectors V and W, V plus W equals W plus V. Plus is associative. So okay. You know what that means. Additive identity. So you see, I'm just going very, very parallel to this. Again, from this you can prove that the additive identity is unique. I won't prove it here. Okay. Inverses, yes, inverse, of course. V plus minus V equals 0. Sorry, I will start underlining later. And I don't, you see, again mention the uniqueness, but again it's unique. Distributed. I'll keep that because I really need to remember to say it, otherwise I'll forget it. Okay. And now you see here, I kept saying A times B plus C is AB plus AC. I did not say A plus B times C is AC plus BC. But now I will need to say that for both in here because now the two things are different. Sorry, I will need to say A plus B times B and A times B plus W. So these are not derivable from each other. But before that, let me see. I think we have already deduced, done various things. Oh, interesting. Okay. The next thing is about scalar multiplication. So, fine, let's do that. Let's write down the properties of scalar multiplication. Yeah, basically, okay. So again, if you have seen something before or you will in Algebra 1, this is basically saying that this is a module over the field. Okay. So it satisfies the module properties, which include the distributive law. So let's write this down. So scalar multiplication satisfies I'll just write them list them here. One is that do I need to say 0 times V is 0? I don't need to say 0 times V is.
No, that can be proven from the axioms.
Exactly. So I do need to say 1 times V is V for all V in V. I need to say A. So now suppose I want to multiply two scalars and one vector. And again, so I have something like, okay, clearly this multiplication is not commutative because you can't switch vectors and scalars. But can it be associated in a certain sense? And the answer is yes, it has to be. If I take A times B times V, okay, then I can do this in two ways. One is I can first act by the scalar on the vector and then by another scalar on the vector. Okay, this is going to be bad. I should keep stars again. Otherwise, somebody might think there's a minus one here and minus three here. Okay, on the other hand, I can also do the following. What is the only other thing I can do? Well, I can first combine these two in the exact associative kind of way. Where I multiply the scalars first, I get a new scalar in the field, and then I act by that scalar on the vector. And the answer is these are the same. It's for all vectors V and scalars A and B. Okay, then there's the distributive laws in plural, because you have that. A plus B times V was A dot V plus B dot V, and A dot V plus W. What is going on? Equals A dot V plus A dot W. So it's the first lecture, sorry, I have to write down all these things. For all, you start writing down these quantifiers for all A and B in the field, V and W in the vector space. Okay. I think that is pretty much it. And then you can derive again nice things like 0 times V is 0. A times this 0 vector is 0. And minus A times V is A times minus V is minus of A times V. All these nice things follow. And I will ask you exercise at some point. But I don't think I seem to have asked you that other thing. Okay, I will write this down. 1 second. Where is a pen? Minus C times V equals C times minus V equals minus of C dot V. Oh, great. I'll ask you that. Apart from uniquenesses of whatever. T. Okay, and then okay, so that's that. Okay, then there are other things. So okay, maybe I should give you examples. Whenever you give a concept, you're supposed to give examples. So let me do that now. Oh, we have till 10 o'clock. Scared I'm already over. So let's do examples. But you see how parallel these things are, right? Wherever you can do a distributive law, you do it. Wherever you can do an associativity, you do it. You insist on it, and so on and so forth. And remember, we did not prove that 0 times the scalar is 0 in the field. But we did not prove it. We did not have it as an axiom. We didn't prove it, but you will in your homework. So similarly, we don't have as an axiom that 0 times a vector is 0, or scalar times a 0 vector is a 0 vector. That we can prove. Okay, so otherwise, everything else is parallel. Associative, additive, identity, and inverse. Okay, great. So now, no. One thing I wanted to do before that is I wanted to check that I haven't actually forgotten the vector space axiom. So let's see, where is vector spaces here? Vector spaces, chapter 2 of Hoffman-Kunz. Vector spaces. Definitely. Field of scalar set of objects called vectors. A rule called vector addition. Hoffman-Kunz keeps saying unique, unique, unique. You don't need to say unique. You can derive it. When say a rule called scalar 1 dot a. This thing is perfect. Okay, very good. Okay, great. So now examples. So first of all, the fields. Okay, so first of all, real numbers. At some point, I hope, at least for the math majors and the PhD students, that you see the definition of real numbers. Okay, there are two different ways one defines them. One is using Cauchy sequences or rationals, and one is using Dedekind cuts. And I hope you see both of them. It's actually fascinating to construct real numbers. I mean, the point is, it's very easy to construct integers. And that's what they say, right? God created 0 and man did the rest. And so it's very easy from 0 to create in positive integers, and that from that to create negative integers, and from that to create rational numbers. Fractions is easy. Getting from fractions to reals is hard. Okay. Okay. The next is, of course, these complex numbers. These are all fields. And as far as complex numbers goes, okay, I'll give it to you as a homework problem. How do you multiply and divide two complex numbers? So I'll give you actual definitions and so on. Next is rational numbers. These are some of the fundamental number systems. Okay, so can anyone maybe, just as a fun warm-up, can anyone actually write this down? So assume that you know what are integers. Okay, so you're allowed to assume that you are allowed to assume familiarity with integers. Describe for me the rational numbers as a set description.
As P by Q, where P and Q belong to side.
Yeah.
Q not equal to 0.
Oh, that's right. So this is the rational number. Set of all ratios of integers where the denominator clearly cannot be seen. Okay, great. And then now you have other more interesting things, such as this one. There are various people give various names. It's either FP or Z mod PZ. Some people write Z subscript P, but that actually is somehow wrong. Okay? And when you learn higher algebra, you will see that. But this is a set of residue classes or remainders modulo. Division by P, where I haven't told you what P is, where P in Z, sorry, Yeah, let me even say P in Z. I'll make it better. I'll say it's a number that's bigger, strictly bigger than 1 is a prime number, is a prime integer. Okay, so and if you've ever seen this modular arithmetic, right, like what clock, it's called clock arithmetic, colloquially, right? So if you take, let's look at numbers modulo 5, meaning what is the remainder when a particular number is divided by 5. So 99 is equal to 4 mod 5 because subtract 95 is a multiple of 5 and you get 4 as the remainder. 99 is also equal to 99 mod 5. It's also equal to -1 mod 5 and so on and so forth. So you basically keep circling around. Once you get to 5, you reset the clock to 0 and you keep circling around. Now the nice thing is that these numbers respect exactly the same laws. So 99 is 4 mod 5. Mod 5. 21 is 1 mod 5. Let's say 22. It looks less non-trivial. Now if you add them up, then you would get the same remainder when you add these guys up. The nicer thing is what happens when you multiply them. Then you still get the same remainder. So then 99 times 22, I don't know and I won't compute it, is actually congruent to 8 mod 5 because it's 4 times 2. But now 8 is the same as 3 mod 5. So without actually doing long multiplication, I can tell you that the remainder when you divide this by 5 is 3. And this is the source of all kinds of basic Olympiad problems like compute what are the last 2 digits of 2021 to the 2021. And then people work something out using modular arithmetic. I certainly remember doing all these things. But another fun application of modular arithmetic is you can actually come up with divisibility tests for any number in any base, not just base 10, using some kind of looking at the digits of any. So there are lots of, but there are far more important applications as well than just look at divisibility tests or Olympiad problems. This has been used in a bunch of fundamental ways in mathematics, really fundamental. But the point is, this is a field. So for the remainders mod 5 is a field. And it's very easy to see that you can add two remainders mod 5. So 4 plus 2 is 6, 6 is the same as 1. You can add 2 residue classes mod 5. You can 0 is just every number divided by 5. Every multiple of 5 is the 0 scalar in this field, and so on and so forth. So, by the way, there is a very precise meaning of this notation. This is an additive group, abelian group. This is a normal subgroup, and this is the quotient group. Okay, that's what this means, formally speaking. But informally, it's just a set of remainders mod 5. And so the point is, if you have 99, which is 4 mod 5, and 0 or 5, let's say 5, which is 0 mod 5, when you add them up, you get 99 plus 5 is 104, but that is still 4 mod 5. So 4 plus 0 mod 5 is still 4 mod 5. So 5 or 0 or 10 or 15 or minus 5, all of these are like minus 20, etc. All of these set of numbers, this entire subset of numbers, if you will, is the 0 element in this field. This entire set of numbers is another element in this field. And basically, there are only 5 elements in this field. All numbers which leave a remainder of 0, all numbers which leave a remainder of 1, all numbers which leave a remainder of 4. These are the only 5 numbers in this field. So this is a field of finite size. This has only finitely many elements. I already told you basically it's easy to see everything, all the field axioms are satisfied. The only one that's not trivial to see is the reciprocal axiom. But that is also not hard to prove. The point is, let me just tell you why the reciprocal axiom works. That's the only non-trivial one. But the first observation to make is note Fp is a finite field. With P, which in general it has P elements. All the different remainders modulo P. 0, 1, 2, 3 till P minus 1. These are all the possible remainders. Okay, now maybe I won't call it a note, I should call it a fact. And I won't prove it, but I will just tell you sort of the provable. So, not proving, but let's see a sketch of proof. of reciprocals. I mean 1 over that inverse. So the scheduled proof of the reciprocals is the following. And I won't prove it just for phi, I'll prove it for p. So suppose you have a number that is not 0 in Fp. Okay, so given n not congruent to 0 mod p, this is an integer which is not divisible by p, that's all right. But what does that mean? It means that n is coprime to p. Because p does not divide it, so therefore the only common factor is 1. Okay.
Now, Desart's lemma is a result of this.
Sorry, which one?
Desart's lemma, there exists integers a and b such that na plus pb equals to 1.
Exactly. So I mean, I'm going to use as a black box that result, which says that whenever two integers are coprime, you can find a linear. If two integers n and p are coprime, you can find two other integers alpha beta, so that alpha n plus beta p is 1. It's a linear combination. Therefore, there exists, let's say, alpha and beta in integers. Maybe let's not call them alpha beta. Let's call them integer names. Let's say p and q, like the rationals, such that P, oh god, not P and Q, let's call them R and S. P is already here. So R n plus S P equals 1. But now take modulo. So then R mod P. So what does that mean? If you take remainders, if you divide by P, then this is already divisible by P. So that means that Rn is 1 mod P. And therefore this guy is the reciprocal. Great, R actually stands for reciprocal. Okay, it worked out pretty well. I did not think of that. But yes, R is the reciprocal of this number and modulo P. I'm not saying it is 1 over n, because though that cannot be an integer. But it is indeed, unless n equals 1 itself. But it is indeed the reciprocal modulo. Okay, so that's I just said it's a sketch because of this thing. I mean, I didn't prove this for you, but obviously in a course like this, you are allowed to assume such things. So, okay, anyway, so now let me end. I told you that I would tell you a few other things that we will see in this course. So first of all, I gave you the definition of a field and of a vector space. I should give you definite examples of vector spaces, but let me first tell you two things that I will. Okay, no, maybe I will give you examples of vector spaces first, because my second fact. Actually, both of these facts are written purely in terms of fields, but they actually are true because they are in terms of vector spaces. You have to think of them in terms of vector spaces. So let's say vector spaces. For concreteness, because it's the first day today, I will just do it over R. Okay. Oh. This was correct and this was also correct. These two examples are examples of fields, but they are also vector spaces over the real numbers. Why? For example, so I won't tell you why for real numbers, but here, for example, you could do something like this, right? So a real number alpha times a complex number, let's say beta plus I gamma. So I, of course, here is the square root of -1. Complex number. This is defined to be, the definition of this would be alpha beta plus I alpha gamma. So that's clearly a real number. Now you have to verify that this satisfies the axioms of scalar multiplication. You have to verify similarly that if you add beta plus I gamma plus beta prime plus I gamma prime, if I define this thing to be beta plus beta prime, you know what it is, of course, plus I times gamma plus gamma prime, then this satisfies the axioms of, and so on and so forth. So, okay, so this is an example, this is a genuine example of vector space over the real numbers. But then there are other examples. So, for example, you have of course seen this in your multivariate calculus. Rn for any integer n is a vector space over R. I mean, you have seen the example, you may not have seen that it's a vector space. So, in fact, for n equal to 1, you get this, for n equal to 2, you get this. This is R and this is R. And then we will get to the basis and dimension later again. Rn is a vector space. That's how you typically we write a backslash to say over R. So meaning again, so what is Rn? It is the collection of A1, A2, An such that Ai, let's call it Aj belongs to R for all j. Right? So how do you add two vectors? You add them component wise. Actually, I will keep writing these with transpose. So transpose just means that instead of looking at them as a row vector, I look at it as a column vector. Okay? So A1, A2, An transpose plus B1, B2, Bn transpose. Should really start over here. So if I have two such vectors, then of course I add them component wise, and this is all basic stuff. So you have all seen this. And how do I scalar multiply? If I have a real scalar alpha and then I want to multiply it, of course I also multiply it component wise. So it's alpha A1, alpha A2, alpha An. And I keep a transpose through. So this is how this is why it's a vector space. But there are many others. So here is another vector space I will tell you. These are the very basic ones. These are also finite dimensional. Now let me tell you some infinite dimensional vector spaces. What does infinite dimensional mean? We will see that in the course. Okay, so 4 is let's look at the set of all functions from let's say 0, 1 to R. This is like a calculus kind of thing. It's called a function space, and it's a this is the set of all functions from I don't even need the interval to be closed. I could have any set. I could look at the functions of the rational numbers throughout. It's not even an interval. Aha, in fact, why am I doing this? I take any set S here. It need not even be inside the real line. It is any set that you want. It could be a set of size 3. The key point is that the domain is a field, in fact R. Therefore, it's a field. Therefore, this is a vector space. Right? So, for example, if you want, you know how to define f plus g. F plus g at any point S is defined to be f of s plus g of s. This is the addition. Similarly, minus f would be minus f of s. And similarly, alpha times f. So, what is this? F is a vector in here. So, f is a function from S to R. Alpha is a scalar in the real line. Let's call this V. So, f is in V. And this better be a new element in V. This better be a function from S to R. So, I have to tell you how to define it on an element of S. And so, the way to define it. So, when I say colon equals, it means I'm giving you a definition. Colon equals. Okay. And the obvious guess, which would be correct, would be alpha. So first operate by f on s, this is a real number, then scalar multiplied by alpha. And yes, this gives you a vector space. This satisfies all the axioms of vector space. So for instance, 1 times f at s would be 1 times f of s, which is just f of s. So 1 times f is a function which exactly agrees with f at every single point with s. That means it's the same function itself. Right? So it's a bit subtle, this distinction, but it is absolutely true that 1 times f is f. Okay, so these are examples of vector spaces. And now let me end by telling you that I remember in the middle of the class I told you some of the things we will see. Like every polynomial of degree 6 has exactly 6 roots, or you can solve differential systems of equations. X prime equals 5x plus 7y, y prime equals 7x plus 5y. Here are 2 other things that we will also see. To return to that discussion, I don't even remember what examples numbers they were, so I'll just call them m and m plus 1. For some integer m, I don't remember what that m was. But fine. So what we will also see is the following. So I told you that the field, there is a field of size P of the remainders mod P. Rather, in particular, there is a field which has finitely many elements, and yet you can add, subtract, multiply, divide by anything non-zero. So what are all the possible sizes of fields which are finite? So let's say if F is a finite field, then F necessary. So can there be a finite field of size 6? Can there be a finite field of size 27? Can there be a finite field of size 256 or 1024? If you like computer science, right? So the point is, the answers are, this is, if F is a finite field, then the size of the field is always a pure prime power. Okay? For some b bigger equals 1, positive integer, and prime p bigger equals 2. Okay, so in particular, you cannot have a field of size 6 because 6 is not a pure prime. But now, can you have a field of size 27? This doesn't say that you can. It says that you can't have it of size 6. And yes, the answer is you do. I don't know. This is for conversely, I'll say that. For all P and D as above, there exists a field with the size of the field equals d power d. It's even better, there exists a unique field. There are not two different fields, meaning that you can, given any two fields of the same size, you can find a bijection of sets that goes from one field to the other, so that then the field axioms also go. If the bijection is like, let's call the bijection G of alpha. So G of A is A prime, G of B is B prime, and so on. So you have the sets A, B, C, D, that's one field. A prime, B prime, C prime, D prime, another field. You can name the things as A prime, B prime, C prime exactly corresponding to A, B, C, such that A plus B, if you take the prime, if you come here, that is exactly A prime plus B prime. If A plus B is C, then A prime plus B prime is C prime. If A times B is C, then A prime times B prime is C prime. So there is a bijection of sets of the two fields which respects the field axioms. If A inverse is B, then A prime inverse is B prime. Things, if the 0 prime is 0 prime is 0 prime, 1 prime is 1 prime, and things like that. So okay, so there is essentially a unique field which you will see in algebra 1 at the end of that class, or maybe in algebra 2, I don't remember now. The syllabus got changed. So that is one thing. Yes, that for every prime power, there is a field, a unique one in fact. For every non-prime power, there is no field with that size. But to prove this, we will have to use the notion of a vector space over a finite field. So we will need vector space, and there's a reason why I called it D. The D stands for the dimension of that vector space. Similarly, the field, so now in particular, I know that we have fields of size 16, 8, 4, 2, I don't have a field of size 1, right? But the field, let's call it F16, contains F4 and F2, or F2 and F4, let's say. By the way, when I say F anything, I mean the field of that number of size, number of elements, but it does not contain F8. Why? Again, the answer has to do with dimension and basis, or the dimension basically. Right? So the field of 16 elements does contain the field of 2 elements, the field of 4 elements. We know that the field of 8 elements exists, but that does not sit inside the field of 16 elements. Okay, so we'll see that next time. Okay, so I think this is already like 9:58. So as I said, today the only thing that you need to take away maybe are some example, the definition of a field, the definition of a vector space, which you can again find everywhere online. Examples of fields and examples of vector spaces. As for the rest, like these finite field stuff, I mean, I will just assume this part. I will assume that there exists such a field. If I ever need to use it, this part I will actually prove that if you have a finite field, the size of it must be p power d for some unique p and unique d, obviously. So that part I will actually prove. So this part, if we ever need it, we will assume, but that is something for algebra 1. Okay, so before we close, are there any questions? And if not, then yeah, we are all on the mailing list. I should have said that if you did not receive an email from me today morning, then clearly I did some gapla in adding it to the mailing list. So please email me and remind me to add you to the mailing list, and I will do that. Okay. Of course, I've already, because you're here, I assume you already received you're already on the team, but I would like to add you to the mailing list as well. So please let me know by email if you haven't received an email this morning from me with the class time and so on. Okay, thanks. So we'll stop here. I'll stop the recording first.